Okay, today we are studying sections 10.2 and 10.3, so we're looking at products and quotients of functions, as well as compositions of functions. So let's start with a couple blanks here. To combine two functions f and g of x, multiply or divide as follows. So the product of functions would be f of x times g of x, which can also be written as f times g of x. Quotient of functions is f of x over g of x, which can also be written as f over g of x. Alright, so let's take a look at this in motion here. Determine the product of functions. So we're given two functions, f of x equals x plus 2 all squared minus 5, and g of x equals 3x minus 4. Determine the product of these two functions, state the domain and range. So the product is, if we take f of x as is, and we multiply it by g of x as is, so we have x plus 2 all squared, which I'm going to expand right now to be x plus 4x plus 4 minus 5, and then we're going to multiply this thing by 3x minus 4. Sorry, this should be x squared. You can already see that this thing is going to be cubic because we're going to multiply an x squared by an x term. I'm going to simplify this a bit more and then continue with the multiplication. So plus 4 minus 5 is minus 1. Multiply it by this thing, so we just distribute every term into every other term in the brackets here, and we get 3x cubed minus 4x squared plus 12x squared, so that's that times that, minus 16x minus 3x plus 4. Group your like terms. Sorry, this should have been cubed. Group your like terms, so 3x cubed now minus 4x squared plus 12x squared will leave us with positive 8x squared. Minus 16 minus 3 will leave us with minus 19x, and then plus 4. And this is our new function, a cubic function. Okay, so let's try the next one. Oh, that was the only one on that page. Hooray, we're done. So go ahead and try this. Multiply these two functions together, see how you do. When you come back, the answer will be here. Hit pause now. There you go, hope you did great. Oh, and I forgot to state the domain and range of my last function. So let's go back. We had this as our new function right here. Okay, so the domain and range, now this is a cubic and it has a positive lead coefficient, so we know that a cubic with a positive lead coefficient will, go something like that. So the domain is going to be all real numbers. You can just see from the graph, you know what cubic graphs will do. And the range is also going to be an element of all the reals. So there you go. Okay. So now we're going to determine the quotient of two functions. So we look at these two functions, and we're going to do g over f. Now, if we look at these two functions originally, we're going to have to state the domain and ranges of the composite function, or not the quotient function at the end. This one is a quadratic. We know that it has a domain of the reals, so x is an element of the reals. And this one is linear, and x will also be an element of the reals. Okay. So we'll see what happens when we look at the domain of our final function here. So we're doing g over f. So here we go, we start with g, 2x plus 6. We're going to divide that by x squared plus x minus 6. Now, let's do some factoring. We have worked with rational equations in the past and rational functions, so we know how to deal with these things. This can be factored as 2 times x plus 3. Your denominator is a quadratic. It can be factored as x minus 2 times x plus 3. Now, here we have a rational function where the x plus 3 factor will cancel. What this means is that when we have a canceling factor, we have a point of discontinuity. So hopefully you remember that from our rational functions unit. So there will be a point of discontinuity. When x equals minus 3, there will be a hole. Okay. And this factor doesn't cancel off at all, so x minus 2, so whenever x is 2, when x equals 2, we are going to have a vertical asymptote. Okay, so you remember this stuff from before, and this means that in our new domain, x, such that x cannot be the values minus 3 or positive 2, but otherwise it can take on any value, an element of the reals. Okay. Now, all that was brought about because the denominator is not allowed to be 0. So whenever we have f in the denominator, it's these values that can't be 0. If we put g in the denominator, it would be the values of g that made it 0. Okay? So sketching the graphs, let's see. Oh, no, not yet. Okay. Sketching the graphs right here. This is what the original functions look like. So f of x, quadratic, g of x is this linear one. And in order to sketch the graphs, we would use basically a table of values. So since we're doing g divided by x, figure out a whole bunch of values for x to plug into both functions. So we plug in minus 3 into g, and we get 0. Plug minus 3 into f, and we also get 0. 0 divided by 0, okay, this doesn't exist, this is not a real thing. So here we have doesn't exist, and you notice on the graph here that when x is minus 3, we have a point of discontinuity, or a little green hole there. Plug in some more values. So here we get 2, here we get minus 4, g divided by x, that will give you the value in this one. And that will work for all of them. 4 divided by minus 6 will give you minus 2/3. 6 divided by minus 6 gives you minus 1. So all you have to do is take any y value in the g function, divide it by the y value at the same x location in the f function, and you will get the new value in the h function. So this is what it looks like a little clearer on the graphing calculator. Okay. So here's another your turn for you to go ahead and try. If it doesn't go so well, especially with the range part, you can ask me about this tomorrow. Here are your answers. Yeah, no, maybe just don't. Okay. So there are your answers. Alright, now we're moving on to composite functions. Composite functions are functions that are formed from two functions in which the outcome or output or result from one function is used as the input for the next function. So we basically solve one function and get a number and then plug it into the next function. So composition of these is defined as f of g of x. So that's how we say it, f of g of x, when g is inside like that, and is formed when function g is substituted into the equation of f of x. We'll see what this looks like in a minute. F of g of x exists only for those x values in the domain of g of x. So we determine the domain of g of x, and where g of x is in the domain of f of x. Now this is a difficult definition to understand. We'll clear it up in a couple minutes here. Another way to write this is like this. Looks like the word fog. The reason we do a big open circle is so that we don't mistake it with multiplication of two functions. Okay, this is multiplication of two functions. This is the composition of two functions where we plug g inside f. And similarly, if you wanted to do it the other way around, it would look like that if you wanted to plug f inside g. So let's see what this looks like. So f of x is 4x, and g of x is x plus 6, and h of x is x squared. We want to determine each of these composite functions. F of g of 3. So we start off on the inside and work our way out. So we'll start off with g of 3. So g of 3 comes from here, and this would be 3 plus 6. So g of 3 is 9. So we want to know f of g of 3. So once we've found that g of 3 is 9, we want to know f of 9. So f of x equals 4x, f of 9 equals 4 times 9. So f of 9 equals 36. Now this is only one possible method to do this problem. Let's take a look at another one. So in that method, we solved g of x first, and then we plugged the outcome into f of x as an input. But if we wanted to just take g of x and plug it in our f of x before we solve anything, what we would do in f of x, wherever we have an x, we replace it with all of g of x. So instead of x, we write now x plus 6. Now let's see if 3 will give us the same value. So 4 times 3 plus 6 is 4 times 9, and of course we get the exact same value as before. So let's try the next one. G of h of negative 2. So I'm going to take my h, and for every x, so g of h of x will be wherever I have an x in g, I'm going to plug in an x squared, because that's what h of x is. So g of h of x is the same as g of x squared. G of x squared is, I replace every x in here with an x squared. So it looks like that. So g of h of minus 2 then will be if we replace all of our x with minus 2, and it looks like this, minus 2 squared plus 6, which is of course 4, plus 6 is 10. Alright. Finally, h of 2. Yes, we can plug this same function into itself. So let's see what this looks like. Start on the inside. Let's just solve h of 2 first. So h of 2 equals 2 squared. H of 2 equals 4. So now we take this and we plug it into the h function. So h now of 4 equals, okay, h is x squared, so we go 4 squared. H of 4 equals 16. And this is the result of this. Now, if you want to see it the other way, where we do the function first, we would take our h function, which is x squared, and instead of h of instead we do h of x squared. So wherever we have an x in our original h function, we replace it with an x squared. So we go x squared and then square it, which would be x to the 4. Now, of course, when we plug in 2, we have 2 to the 4, which is, of course, 16, which is what we got doing it with the other method as well. So here's another your turn. Give it a try. As always, find the answers when you come back. There they are. Alright, now we're going to compose some functions with restrictions. This is where it gets a little bit trickier. So, we're looking at these two functions. Now, right away, it wants us to determine f of g and then g of x. And then it wants us to state the domain of all of these things. So, f of g. So we take f of x, and instead of an x, we're going to fill it with whatever the g function is. So f of g of x, we're going to replace every x in here with this. So it becomes f of x squared, which becomes the root of x squared minus 1. So that's f of g of x. Now, g of f of x works the other way. We take whatever f is, and we replace every x in g with it. So g becomes g of root x minus 1. So wherever we had an x here, we replace it with a root x minus 1. And then that was x squared. So that becomes that squared, which of course just becomes x minus 1. Now, let's state the domain of all of these functions. So consider this function. Now, we're not allowed to take the square root of a negative number. So anything that makes this negative is not allowed. So x minus 1 must be greater than or equal to 0, which means x must be greater than or equal to positive 1. So that's the domain of f of x. Now, the domain of g of x is anything. Anything is allowed in g of x. So x is an element of the reals. This is the domain of g of x. But what about our composite functions? X cannot be anything less than or equal, less than 1 in this function. So when we take and we plug in g into our f function, we still are not allowed to use any values in g that make this whole thing end up being less than 0. So whatever makes this a negative number. So you can take this thing, once g is plugged in here, and this has to be greater than or equal to 0. So x squared has to be greater than or equal to 1, which means take the square root x. Now we would say must be greater than or equal to plus or minus 1, but that doesn't really make sense. Now, when we divide by a negative in an inequality, we always have to flip the sign. So this actually becomes, x is greater than or equal to 1, and x is less than or equal to -1. Now I'll show you here why this makes sense. If we choose a value of x that is, let's say, exactly 1, and we plug it into this function, we get 1 squared minus 1, which is 0. We're allowed to take the root of 0. That's okay. Now let's plug in -1. We plug in -1, and we get -1 squared is 1 minus 1 is 0. And again, that's allowed. Let's try a value in between these two. So let's say like 0. So if x is 0, we plug in 0. 0 squared is 0, minus 1 is -1, and now we're trying to take the root of a negative number. So nothing in between these two values works. So if we had a number line, this was 0, 1, minus 1, kind of a poor number line, but all of our values are going to work in this region, okay? But nothing is going to work in this region. And you could test some other ones, but you find out that you just end up getting negative values that you're trying to take the root of. So basically what this is saying is that any value of g that makes this not true, so any value of g that we plug into g and then into x that messes this up is not allowed in the domain of the composite function. So for example, we said that 0 is not going to work. Well, let's see what happens. If x is 0 in g of x, then this is 0 squared, and we plug 0 in here, and we get 0 minus 1. So you can see that that doesn't work. So what that means is that values in the domain of g are okay to try, but if they end up not working with the domain of f of x, then they don't work at all for the function, or for the domain of the composite function, sorry. That one will probably need clarification in class tomorrow. Let's take a look at this composite function, g of f of x. So, see if there are any restrictions on this one. Now, we know that we're not allowed to use, in f of x by itself, we're not allowed to use any value less than 1. So, in the original f of x, these are the only values that are allowed. Now, are there any values in this domain that don't work for this? Well, we know that absolutely any value will work in this domain. So it doesn't matter what we plug in from this, within this domain into here, we're going to get a real value that's okay to use. So the domain of our composite function then is only restricted by the original function. So the domain of the composite function then is x must be greater than or equal to 1, but otherwise is an element of the reals. So let's just see if we can summarize some of those. I left this stuff up. There you go, the domain of the original two functions. Now, the domain of f of g is a set of all values of x within the domain of g, for which g of x is in the domain of f. That sounds wordy. Let's break it down. The set of all values of x in the domain of g. So, in the domain of g are all values of x. All values of x are possible. But there are some values in this domain that don't work for f. For example, within this domain, anything that makes f less than 1 is not going to work. So we figured out that that would be anything that was between -1 and 1. Because g of x, the function is x squared, anything that's between -1 and 1 is going to give you a fractional number or a decimal, and when we subtract 1 we're going to be trying to take the root of a negative. Sorry if that's not very clear, we'll talk about it in class tomorrow. So this is the range of, the domain of the composite function, and let me show you what it looks like if we graph them. So this is f of x, this is g of x. Now if we do f of g of x, we replace this x with whatever g of x is, so that becomes x squared. And you'll see that the domain goes from here this way to infinity, and from here this way to -infinity. So nothing in here ends up working. Alright, let's move on. Give this one a try. If it doesn't work out, we'll talk about it in class tomorrow. There you go. Alright, so let's determine the composition of two functions. This will go pretty quickly. We're going to state the domain and range of each of these. So f of g of x. So f of g of x means we take g of x and plug that value in for every x within the f of x function. So this ends up being f of x squared, which is, of course, x squared plus 1. So we've replaced this x with whatever g is. Okay, now g of f of x, which is b. So take f of x and plug it in for every x within g. So g then becomes g of x plus 1, which used to be x squared, now it's x plus 1 squared. F of x. So we take f of x and we plug it in for every x in f of x. So it becomes f of x plus 1. So wherever we had an x here, we replace it with an x plus 1. So this becomes x plus 1, where we used to have just an x, and then plus 1, which of course simplifies to x plus 2. G of x becomes g of x squared. Now g was originally x squared, so if we replace each x with an x squared, then we take that and we square the whole thing, and we get x to the 4. Okay, so let's state the domain and range of each of these things. This becomes a quadratic function with a vertical shift of 1. So the domain in a quadratic is x such that x is an element of the reals, and y is going to, this opens upward, so y is always going to be greater than or equal to positive 1, but otherwise it can be an element of the reals. Let's just clear a little space here. That one's done. So the domain and range of this one. This is also a quadratic. So if we expand this thing, we end up with x squared plus 2x plus 1. So this is also a quadratic. Now it's going to have a vertex at -1 and 0. So the vertex is going to be at -1 and 0. And it opens upward. So the domain, as is true for the vast majority of quadratic functions, x is an element of the reals, and since your vertex has a y value of 0, y, and it opens up y such that y is always going to be greater than or equal to 0, but otherwise it's fine just being an element of all the reals. You can graph them to double check if you'd like. Finally, this is a linear function. Linear function that will have a y-intercept of 2, okay, which means it'll go something like that because it has a slope of 1, and your x is going to be an element of the reals, and your y is going to be an element of the reals. Easy one. I like it. This final one, we ended up with a quartic function. Now, a quartic function will look a lot like a quadratic. This one opens upward, has its origin at 0 and 0. It just opens up a little wider than your typical quadratic. So it'll look like that. And again, your x for this quartic, these will go on forever to the left and right, albeit slowly. They will. It's an element of the reals, and your y is going to be, has to be greater than this point, which is 0. Y is greater than or equal to 0, but otherwise an element of the reals. No problem. So go ahead and try this one. Come back and check your answers. There you go. Okay, now determining the original functions from a composition. This is the last thing we're going to do today, so let's see how it works out. We are given a composite function here, and we want to break it down into two individual functions. So what we need to do is we need to look for anything that's common in each of the terms, or in more than one term. So if we just say let g of x equal x plus 2. Sorry, that should be x minus 2. Let g of x equal x minus 2. Now we can rewrite this thing, h of x, as g of x squared plus g of x plus 1. Now, if it looks like we just have something squared plus something plus 1. So if we just say f of x would be x squared plus x plus 1. Now you find out that if we plug this into each of these for each of the x's, we would end up with the composite function that we started with, and that's how we know that we've done it correctly. This one, there are going to be more than one possibilities for this one, but I will show you one. We could do a really simple one where we say let g of x equal x cubed plus 1. So if g of x is x cubed plus 1, then f of x would be root x. So that when you take f of g of x, you take this and plug it in for x, and then you end up with that function. So this is one possible solution. But there are lots that would work here. Maybe not lots, but there's certainly more than one. So for example, if we say let g of x equal x cubed, then f of x would have to be the root of x plus 1. So if we replace this x with g of x, then it would be root of x cubed plus 1. And that is also a possibility that works there. Okay, so that's how we work backwards. Go ahead and give this one a try. There you go, there's your answers. And that's all we're doing for today, so I'll see you in class tomorrow.